Okay, so in the next video we're looking at this very interesting phenomenon whereby I could start with a blue triangle, reference triangle, which is going to remain stationary, and I can move a point M on its plane, okay, somehow, and I can define three subtriangles by connecting M to the vertices of the original triangle. Okay, so here's M, and I can define these three subtriangles that together triangulate, so to speak, the original triangle, and for each individual triangle I can compute its orthocenter. So here are the three orthocenters, x4, x4, and x4, corresponding to each one of these subtriangles. Then I can do a weighted average of these orthocenters and report the so-called orthocenter of mass, which in this case is going to coincide with the orthocenter of the original triangle. Now, one curious fact that we reported in the previous video was that if I move M around, the area of the triangle that connects the sub-orthocenters, the 3x4 shown on the screen, the area of that triangle is independent of M. Now I'm actually sliding M up and down. Okay, it's independent of M, and it's equal to the area of the reference triangle, the blue triangle. So this is a family of dashed red triangles which have equal area, whose area is actually equal, or invariant area whose area is equal to the area of the reference triangle. Okay, let's make M now go outside of the triangle. We have this sort of nicer family, sort of less shooting off into infinity family, but you can see here that I'm reporting the area of a family of dashed red triangles and the area of the blue triangle, and that their ratio is equal to 1, meaning that the family of red triangles has an area independent of the position of M. And that's a really neat fact in it of itself. Okay, so as I move M around, I can explore a whole family of equiarea triangles. Okay, very good. Now this video is about another neat property related to the perimeter of these triangles. As you can see here, as I vary M, the perimeter of these triangles is variable. Okay, so before we actually do this, let's do one first remark. Let's take M and make M be equal to the actual orthocenter. So let's move M toward the orthocenter of the original triangle. And I'm going to do this initially manually. Let's scale this up a bit, like so. And I want M to go near x4 of the original blue triangle. So I'm just going to move M around like that, and I'm going to move, I'm going to slide it up a little bit. Perhaps I did it too much. Let's go ahead to 0.05. Yeah, so you can see here that as M approaches the orthocenter, something very neat happens. So let's make it be exactly on top. So now M is exactly on top of the orthocenter. The three orthocenters will sub-orthocenters, right? The orthocenters of the three triangles will magically fall on top of the vertices of the original triangle in such a way that the triangle formed by the sub-orthocenters is equal to the original triangle. So the area equality between the two is preserved. Let's perturb this a little bit. Let's add a little noise to this. You can see here that now M has slid up just a little bit, so that triangle of the orthocenters is slightly different. Now let's slide M a little bit to the right. You can see here now it's actually quite a bit further out. Let's go ahead and make this guy be minus 45. So I'm closer, minus 0.5, I'm even closer. So as I approach it, the orthocenter of the blue triangle, you can see that the triangle of the orthocenters approaches the original one. Now the fact remains that wherever M is, that family has the same area, and for M equals to x4 itself, the two triangles are congruent, like so, and the areas are still the same. Okay, now the phenomenon that I want to show in this video has to do with the perimeter of this family of triangles as I vary my M. Now you can see here that the perimeter is being reported here, and the perimeter of the original triangle is 5.91, the blue triangle, and the perimeter of this dashed red triangle looks like it's a little larger, 5.97. So if I move M further out, you can see that the perimeter is growing of the red dashed. It's now at 6.7. let's now move M outside of the triangle. M is now outside of the triangle. My perimeter is pretty large because my triangle now is very large, right? So if I scale this down, you can see the whole triangle there. It has a perimeter of 11.9 units versus the fixed perimeter of the blue triangle of 5.9. Very well. Now, the phenomenon that I want to show you guys is when these two perimeters are equal. So let's keep moving M out to the right. And at some point, you can see that my perimeter is decreasing, decreasing. And at some point, almost at this position here, the two perimeters are almost the same. 5.94 for the red, dash red one, 5.91 for the fixed blue one. Now, what's going on here? Let's draw the circumcircle of the blue triangle. Here's the circumcircle of the blue triangle. It turns out that if M lies on the circumcircle anywhere, if M lies on the circumcircle, the sub-orthocenter triangle, that is to say the triangle formed by the orthocenters of the three individual triangulation triangles. Now in this case here M is external, so this is not quite a true triangulation, but I do have three triangles, right? I have a triangle formed by M over here and these two vertices, so this is it's an external triangle. Then I have two triangles that are sort of hybrids. They have regions that are internal and regions that are external, but it's sort of a triangulation, a fan triangulation in the usual sense, in that I'm going to connect M to the three vertices, and I'm going to consider the three triangles that are result from that. Now, the remark here is that so long as M is on the circumcircle, the triangle formed by the three orthocenters is a reverse homothency. It's identical modulo a reflection to the triangle, the original triangle. So I can actually move M along the circumcircle, and I can watch that neither my area changes, reported over here, neither my perimeter changes, and that this perimeter is equal to this other perimeter here, to the perimeter of the original triangle. Now there are other more complicated equiperimeter or isoperimeter curves in the space, which are not circles. They are more complicated curves, but there are isoperimeter curves I can walk M on, such that both the area and the perimeter of my triangle of the sub-orthocenters, its perimeter is preserved. Okay, and I'm gonna somewhere post a link to the iso curves that produce that. Okay, so that's the result. You walk M on the circumcircle of any triangle. Let's change this triangle a little bit. Let's make this triangle more obtuse. Let's rotate it a little bit, sort of the blue triangle, and let's see if this is verified for this new triangle here. Now, pretty much, I think sort of a right angle triangle. Let's make it obtuse. Let's move it over here so it's really obtuse. So now I have an obtuse blue triangle, and what I'm going to do is I'm going to walk M along its circumcircle, and I'm going to see if both the area and the length and the perimeter of my dash red triangle is preserved. And it is. You keep getting the same phenomenon. The image of, or the triangle formed by the three sub-orthocenters is a reflection, and homothency ratio equals to 1, but it's actually a reflection of the blue triangle. Therefore, it's going to have the same perimeter. Okay, so let's scale this out a bit to see this whole phenomenon. As I move this around, you can see that as I do that, I get that scaled thing. So it's only along this isoperimeter curve that the two triangles have the same perimeter, but anywhere else I place M, so if I place M somewhere else, it's only the area that is preserved and not the perimeter, as we saw before. So I'll leave you guys with this result. Thanks for your time, and I'll see you on the next video.